Hello and welcome to Mr. Linford's math course. In today's discussion, we're going to be introducing the topic of complex numbers. In particular, we're going to define what complex number is, as well as the complex unit I, and then we're going to use our understanding of complex numbers to simplify negative radicands. So the first thing that we should do is we should talk about what the complex unit I is. So we're going to define I as I squared equaling -1. So this is the definition of I. It is what's called a complex unit. The complex unit. And we are saying that this unit, when you square it, you get -1. So some books would go and they would say that I is equal to the square root of -1. This is kind of going to be the working definition that we're going to use later on. Now, is I a real number? What number could I be? What number squared gets you -1? Well, let's see. -1 times -1 is, oh wait, that's just +1. No, that doesn't work. And then +1 times +1, that's still just +1. So is there any number on the number line that if you square it, you get a negative value? Hopefully you're saying no. And that's because I is not a part of the real numbers. There is no number on the number line that when you square it, you get a negative number. Okay? Instead, we have to now work with things that are called complex numbers, and we're going to work in the complex number system. The complex number system is an extension of the real number system, okay? So I might put that in the definition. An extension of the real number system, where a complex number is of the form a plus b times I, where a and b are real numbers and I squared equals -1. So this is going to be our working definition of complex numbers. They're numbers that are written in this unique form. They have two components to them. They have the real component and they have the complex component. So let's try to break this down a little bit. A plus b times I. A and b are both real numbers. So this is the real component, and this is the complex component. You'll notice that I'm writing this C with a little line through it. That's a symbol for the complex number system. Now, I mentioned that the complex numbers are an extension of the real numbers. So if you imagine the set of all complex numbers, so imagine I have a group of all the complex numbers. I have a set of them. Of course, that's not real, right? Like there's infinitely many. But imagine I had all of them. The real numbers are just a subset of the complex numbers. So we might say that all real numbers are complex numbers, but not all complex numbers are real. Okay? That's what this idea of being an extension of the real numbers means. We've added on extra components. So we've taken all the real numbers, and now we've added on this ability to take the square root of -1. Now we've talked a bit about this. Let's go ahead and let's make some examples. Let's try to actually figure out for ourselves what is a complex number. What is an example of one? So let's write down some examples. a plus bi. Well, a is a real number, so let's just pick a real number. I guess I'll pick the number 5. And then we have to add on another real number. Let me pick 2. And then I have to multiply that by I. This is an example of a complex number. This is a single number. And we have to understand that this is how numbers are going to be written in the complex number system. Again, this is a new number system. We've extended it, right? No longer are numbers singular things like 5 or 10 or 150 or 3/4, right? These are all singular values. Instead of having that, we have to be comfortable with this idea of a real component and a complex component. The real component and the complex component. This makes one given number. In a future video, I'll talk a little bit more about what this implies graphically and how we can picture this as more graphically as opposed to working on the real number line. But for right now, we just need to be comfortable with the idea of how to identify what a real number is. So maybe let's make some more examples of real numbers. We have things like 3 plus 7i. Maybe let's have fractions in there. 1/2 plus 2/3 times I. We could even have things like the square root of 2 plus pi times I, because the square root of 2 and pi are real numbers. You could even have negatives. -3 minus 5i, because negative numbers are still real numbers. And nowhere in the definition did I say they can't be negative. So that's even allowed. Something I'm curious about, though, is the statement I made before that all real numbers are also complex numbers, but not all complex numbers are real numbers. So it gets back to this idea that the complex numbers are an extension of the real numbers. So we need to think to ourselves, okay, if I have a real number, it is also complex. So let's pick the number 5, for example. This is very clearly a real number. It's on the number line. How can I write 5 so that I can also say it's a complex number? Take a minute, pause the video, and think to yourself, if 5 is a real number, then by definition, it's also a complex number. Well, how can I write it so that I could write 5 as a complex number? Well, hopefully you're going through and you're seeing that if we are going to represent 5 as a complex number, we need to have a real component and a complex component. Sometimes people, by the way, often call this the imaginary component. I'm going to try to avoid that phrasing as best I can. I don't really like the terminology, the imaginary component, but it's published in several textbooks, so it's kind of just not the best naming convention for these things. So I'm going to call these the real components and the complex components. So if I'm taking the number 5 and trying to represent it with real and complex values, I can represent the real value as 5, because it's a real number, so there's 5. But what would the complex component be? Well, just say to yourself, are there any complex values here? Do you see an I at all? Hopefully you're saying no, otherwise get your eyes checked. So our answer is 0. We can say that 5 is also the same thing as 5 plus 0i. This is why we're able to say every real number can be written as a complex number. It's just the complex component is always set to 0. So if you wanted to, you could take, for example, 7 can be written as 7 plus 0i. 10 can be written as 10 plus 0i. These are numbers that have a real component, but no complex component. There's a unique graphical way of seeing this, which we'll talk about later on, but what I mostly need you to understand here is have this ability to write complex numbers and to work with them in this form, okay? Now, one of the things that we're using these complex values for is we need to be able to simplify radical expressions that have negative radicands. Before, we couldn't do this, right? If we said to ourselves, what is the square root of negative 25? We would say that's not possible. There's no number. Because any number squared, whether it's positive 5 times positive 5, or negative 5 times negative 5, we always ended up with a positive number. We never got a negative value. And we searched, we thought any number on the number line this is going to be true for. Any number you square in the real number system, you will never get a negative value. But now, with this idea of complex numbers, we can get a solution for this. It might seem a little like we're making things up as we go along, which sometimes it feels like we do in math, but there's a very creative way that we're going to go about doing this, okay? Take a minute, pause the video, and try for yourself to simplify this radical expression. And remember, a simplified radical expression will be one that has no negative in the radicand, and the radicand is fully simplified, meaning there are no perfect roots as factors of the radicand. So kind of like just like we did before in the previous work with the square root of 25x to the fourth. So pause the video, take a minute, see if you can meet these two requirements. All right, well, hopefully you're able to work through this problem, and hopefully you're able to see that there is a rather simple way of going about doing this. We remember that we can break up the radicand into multiplication. Instead of having negative 25, what if I had negative 1 times 25 times x to the fourth? We can separate this just like we used to with numbers and variables, but we can even separate the numbers. We can have the square root of negative 1 times the square root of 25 times the square root of x to the fourth. Do we have values for all of these answers? Well, we in fact do. What is the square root of negative 1? Well, we defined this as being I. And what's the square root of 25? Well, that's just 5. And what's the square root of x to the fourth? Well, that's just x squared. So we're able to simplify each component of the radical. Now, here is how I want you to write your answer down. You're going to write your answer as 5x squared times I. I want you to have the number followed by any of the variables, followed by the complex unit I. So if I were to take 5x squared times I and square it, we would get negative 25x to the fourth. You're noticing, or at least you should notice, that this is incredibly similar to what we did previously when simplifying radicals. All we have now to do is to take the square root of negative 1. All we have to do is include an I in our final answer. And the reason for that is because this is a complex number. 5x squared I is not a real number. This does not exist on the number line. You're not going to find it on the number line because we said it's not possible in the real number system. We've had to extend to the complex number system. So be comfortable when you have negative values in the radicand, your answer better have an I in the final solution. So let's go ahead and keep practicing this. Pause the video, take a minute to yourself to see if you can go and break down these negative radicands. All right, well, hopefully as you're going through these problems, you're starting by separating them so that you're taking the square root of a negative value and then separating everything else to just simplify those values separately, almost like we did before when simplifying radicals. So we have the square root of -1. The square root of 18 broke up into the square root of 9 and the square root of 2. Square root of x cubed can be broken up into the square root of x squared times the square root of x. So let's go ahead and start simplifying all these things down. The square root of -1 is I. The square root of 9 is 3. Square root of 2 doesn't simplify, but the square root of x squared does. It's just x. And then root x is left by itself. Hopefully you're able to get to this part by seeing how you're just breaking down everything pretty much like normal. This is stuff we've done before. This was a problem I would have given you easily before, so you should have gotten this as your solution. The only thing additional that I've done is I've thrown in this -1 value for you to work with. So that's it. Nothing too crazy or complicated, but we want to make sure we're using our notation right, so let's go over how we should write the final answer. Again, I want you to let's start with everything that comes outside of the radical. And I want you to begin with the number 3. Then I want you to list any variables outside of the radical. And finally, I want you to list the complex unit I. These are all the things outside of the radical. I is not a variable. Make that as a big note to yourself. I is not a variable. You do not plug things into it, okay? Think of I as a symbol like pi. Pi is a number, right? It's not a variable, it's a number. Same thing with I. I is the complex unit, okay? So we have on the outside the number, the variable, then I. Then we can write the things underneath the radical. So we have things on the outside of the radical, followed by things on the inside of the radical. And here is going to be our final answer. 3xi times the square root of 2x. Let's try this again, but this time with a little more elaborate of a problem. Pause the video and try to see if you can not only get a solution, but get it in a way that really makes your work nice and organized. Well, hopefully as you're going through this problem, you're starting by trying to evaluate what the square root of the -300 is. I always like to begin by simplifying my radicals down first and then putting them into the problem. So you can see on the side here, I took the square root of -300 and then I broke it up into -1 and then I broke 300 up into 3 and 100. So the square root of -1 is I. Square root of 3 doesn't simplify, don't expect it to, but the square root of 100 is 10. So if we wrote our answer out, we start with the number, followed by I, and then I have what's underneath the radical, root 3. So let's go ahead and let's plug this value in to our expression. We have 2 times, let's see, change colors here, 10i root 3 all over 30. I do like to have my work to the side here, and I like to color code things just so I can see how I'm breaking down each component and how I'm subbing things back in. So let's go ahead and try to simplify this. 2 times 10 is 20. Then we have I root 3 over 30. And we can simplify 20 over 30, divide each by 10 to get 2i root 3 over 3. Here is going to be our final answer. Again, we expect if your radicand has a negative in it, expect your final answer to have an I in it as well. It needs to simplify down that way. Let's try another problem. This time where we're just breaking down a radical, but maybe let's have it where we have several more terms to work with. So let's take 405, and I'm going to break that down into prime factors. So 405 divided by 5. Oh, look, I get 81. Okay, maybe I won't keep going into prime factors because I know I can take the square root of 81. So let's go ahead and let's say, instead of the square root of negative 405, we have the square root of negative 1 times the square root of 81 times the square root of 5. And instead of x to the 7th, let's take x to the 6th and the square root of x, and let's start breaking these down individually. So the square root of negative 1 is I, square root of 81 is 9. The square root of 5 doesn't simplify, but the square root of x to the 6th simplifies to x to the 3rd, and the square root of x just is left by itself. Again, pause the video if you're right here and make sure you understand how to write the final answer. When you have the final answer, always write it as the number followed by the variables on the outside, followed by the complex unit I. Then you can write everything underneath the radical. The reason for this is we really want to have a solid method of how we're going to write these complex expressions, especially if we're going to have to go and add expressions like this with like radicals together, for example. We don't want a bunch of terms mixed up here. So get comfortable with that way of writing things, because now let's try a situation where we have several variables to account for and to work with. Again, this is very normal. In previous work, I would have given you this problem. But now all I've done is I've included this negative. So again, nothing new to work with here. All we have to do is take care of the square root of negative 1. So let's break that up. The square root of negative 1. And then the square root of, oh boy, well, let's see. We have 192. Let's see, that can break up into 2 and 96. And 96 can break up into 2 and 48. 48 can break up into 4 and 12. 4 is 2 and 2. 12 is 2 and 6. And 6 is 2 and 3. So let's see, what do we have here? How many 2's are there? 1, 2, 3, 4, 5, 6. And then 1, 3. So we have 6 2's and 1 3. So for 192, I could say that's the square root of 2 to the 6th power and the square root of 3 to the 1st power. Then we have to work with the variables. Instead of x cubed, I'm going to write x squared, and I have a root x here. Instead of y to the 9th, we're going to have the square root of y to the 8th, followed by root y. And then instead of z to the 5th, let's take z to the 4th and plain old root z. Now, let's go and break these down one by one. The square root of negative 1 is I. Again, we expect that to happen. The square root of 2 to the 6th is 2 to the 3rd. Hopefully you're getting pretty quick with that now. Square root of 3 doesn't simplify, but the square root of x squared is just an x. And root x doesn't simplify, but the root of y to the 8th is y to the 4th. Then we have root y. The root of z to the 4th is z squared, and root z stays as is. So let's go through and let's try to write everything that's on the outside of the radical. Pause the video and take a minute to see how you are able to organize all of these terms outside of the radical. All right, well, hopefully you're starting off with the number. You could say 2 to the 3rd, or we could just say 8. And then you're following it with the variables, x, y to the 4th, z squared. And then you're finishing it off with the complex unit I. Then we can go ahead and write the terms that are inside the radical, 3x, y, and z. Here we have our final solution for how we're going to go and simplify this radical down. Again, this was nothing new. I've given you problems like this before. Only thing different was I added the square root of -1. So it turns out that this problem that we had of simplifying negative radicands that we said was impossible previously actually has a very simple solution. It all comes down to how we go and define this value I and how we define square roots. So I want to bounce back to the beginning really quick. And under this component where we talk about the definition of the complex unit I want us to put a little note to ourselves here, a little suggestion for how we're going to go about simplifying. If we have the square root of -b for some b greater than 0. So let's say you have some number and positive number and you've made it negative. Remember that this is the square root of -1 times the square root of b, which itself is I times root b. This is going to be that general formula we used anytime we go and simplify down radical expressions that have a negative in the radicand. This is key. So make sure that you're able to go about simplifying all of these. If you have any questions, let me know. And let me know if it's a question about working with the negative or if it's just how to go about simplifying one of the radicals. This is great practice for simplifying radicals. It's kind of all that we did already, but this time we just have to tack an extra I in. Let me know if you have any questions or comments by emailing me at klinford, that's KLINFORD, at wccnet.edu. Until next time, take care.